In a world where the Earth is in constant movement, where the lithospheric plates are created and destroyed, ridges and mountains are formed, there can only be one reason. The Earth's plate tectonic geosystem includes the lithosphere, asthenosphere, mantle, outer, and inner core. We stand on the thinnest layer of the Earth, the lithosphere, which ranges from 0 to 100 kilometers thick in mountainous areas. The asthenosphere and mantle range from 100 to 2,900 kilometers thick, with the outer core ranging from 2,900 to 5,150 kilometers thick. The inner core ranges from 5,150 to 6,370 kilometers thick. The layers are differentiated based on density, with the densest materials moving towards the center. This and the correlation between pressure and depth is why the inner core stays solid even though it is under the highest temperatures. The lithosphere is comprised of approximately 12 plates and is constantly in motion as the asthenosphere shifts to support land masses. This diagram shows how plates move across the globe and collide with and pull apart from other plates. The arrows show relative speed of the plates in millimeters per year. Longer arrows are faster moving plates. Arrows that point towards each other cause convergent boundaries. Arrows that point away cause divergent boundaries, and the breaks in the lines separating the plates are transform boundaries. This will be covered more later. These are all caused by the Earth's internal heat engine. The intense heat generated by the formation of the Earth and radioactive decay is trapped within the Earth's core. This heat causes convection within the mantle, which causes hot material to rise as cool material sinks. This process is behind continental drifting, which shapes the Earth's continents into their present form.
Convergent boundaries occur when two plates move towards each other. There are three types of convergent boundaries. The first one we will discuss is ocean-ocean convergence. As oceanic lithosphere moves towards another oceanic lithosphere, one plate will move downward under the other plate. This process is called subduction, and the area in which it occurs is the subduction zone. This forms a deep sea trench on the ocean floor where the plate is being subducted. As the plate subducts, it carries water trapped between sediment grains on the oceanic floor downward into the asthenosphere. The water in the sediment lowers the melting point of the mantle rock and causes it to melt, thus forming magma. The magma begins to rise to the surface of the Earth, and this causes an eruption. Eventually, the lava compiles and forms a volcanic island. The Marianas Trench and islands are examples of ocean-ocean convergence. The deepest part of Marianas Trench is called Challenger's Deep. It is the deepest spot in the world's ocean, with a depth of almost 11,000 meters. As a result of subduction, island volcanoes are formed. They are often strung out in a chain, also known as an island arc. The Marianas Trench and islands are formed from the Pacific Plate subducting beneath the Philippines Plate. In an ocean-continent convergence, the oceanic lithosphere is subducted under the thicker continental lithosphere. This is because oceanic lithosphere has a density of 3.0 grams per centimeter cube, which is higher than continental lithosphere density of 2.8 grams per centimeter cube. As a result, the lithosphere is deformed into a trench off the shore of the continent. This also forms a volcanic mountain belt at the continental margin. An example of ocean-continent convergence is Mount Rainier located in Washington. Mount Rainier is formed from the Juan de Fuca Plate subducting underneath the North American Plate. Mount Rainier lies in the Cascade subduction zone, a long convergent plate boundary, and it is part of the Cascade volcanic belts. It is 4,027 meters tall. When two continents converge, the crust compresses. It crumples and thickens, creating high mountains and a wide plateau. An example of a continent-continent convergence is Mount Everest. When the Indian Plate subducted beneath the Asian Plate, The crust thickened and piled up, forming the Himalayas. The Indian plate is still pushing towards the Asian plate. Thus, Mount Everest continues to increase in height. It currently stands at 8,848 meters, making it the tallest mountain on Earth.
Another type of plate boundary interaction is divergence. Divergence involves the spreading of the lithosphere, which releases magma, caused by the convection of hot materials in the mantle, toward the surface, creating new lithosphere, therefore adding to the Earth's surface area. Divergence occurs in two forms. Continental rift zones separate continental crust, and in the process cause rift valleys, volcanism, and earthquakes. Continental rift zones are often filled with water. An example of this is the Red Sea. The Red Sea in the Middle East was created through continental divergence. As the African and Arabian plates diverged from one another, they widened the gap between Africa and the Middle East, forming a continental rift zone. As this rift was formed, it was filled in with seawater from the Arabian Sea. Oceanic spreading involves the ocean floor spreading apart as convection forces magma into the lithosphere. Oceanic spreading centers form mid-ocean ridges and increases oceanic crust. This process creates earthquakes, volcanism, and rifting. Iceland provides an example of an oceanic spreading center. As you can see, there is a divergent plate boundary between the North American plate and the Eurasian plate, caused by the convection of the mantle beneath the ocean. As these two plates split apart, magma is released. This magma builds up and forms a mid-ocean ridge and eventually the landmass of Iceland.
Transform boundaries are located wherever there is convergent and divergent boundaries. If there are two tectonic plates touching, then there inevitably will be a transform boundary. Transform boundaries are made when two tectonic plates move in opposite directions of each other. Another, more familiar name that these boundaries have are faults. There are three main types of faults that exist in geology today. The first type of fault is the normal fault. A normal fault consists of a hanging wall and a footwall. Once enough pressure builds up between the two moving plates, it will release, causing the hanging wall to fall downward in relation to the footwall. An example of a normal fault in nature would be the Great Rift Valley in Jordan, where the Africa plate and Arabian plate had given us a very nice example. Although referred to as a normal faults are not the most common and usually appear in areas of tension.
The next type of fault is referred to as a reverse fault and is somewhat similar to the normal fault. Instead of the hanging wall being pulled down in this instance, it is instead pushed up and rises above the footwall. Reverse faults often happen in areas of compression. Example of this compression can be seen on the northern boundaries of the Uinta mountain range in Utah. The last type of faulting there is called strike-slip faults. This is when two tectonic plates are moving side by side but in different directions. The best and arguably the most famous example of this would be the San Andreas Fault, which is located in California. In 1906, San Francisco felt the wrath of this fault when it released its energy, resulting in a magnitude 7.9 earthquake. Being able to detect where these faults are, what type of fault it is, and how big the fault is, we can potentially protect areas that are more prone to earthquakes and subsequently save lives.
Because the Earth's surface area cannot change, when divergent plates force convergent plates to subduct into the asthenosphere, the material must be recycled back into the lithosphere in the form of divergent boundaries. This process results in an endless cycle of generating new lithosphere and recycling it. Transforms serve as tension relievers for divergent and convergent boundaries.
That's all, folks.